Hi everyone, welcome to our event. This event is brought to you by DataTalks.Club, which is a community of people who love data. We have weekly events and supposed to go to the next slide. Yeah, we have weekly events and today is one of such events. If you want to find out more about the events we have, there is a link in the description. Go there, check the link, and you will see all the events we have in our pipeline, which is currently not a lot because we, like everyone else, is going to have holidays soon. But yeah, there is at least one, I think. So the event we currently have in the schedule is for the course we're going to have soon about data engineering. So there will be a workshop, so check it out. And do not forget to subscribe to our YouTube channel. Very important. This way you will stay up to date with all the events we have, all the streams, and you will get notifications about them. And last but not least, we have an amazing Slack community where you can hang out with other data enthusiasts. So check it out too. During today's interview, you can ask any question you want. There is a pinned link in the live chat. Click on the link, ask your question, and we'll be covering these questions during the interview. And I think like my Zoom says that my screen share is loading, but I can see my screen from YouTube. So apparently screen sharing worked, right? That's better. Anyways, Rob, are you ready to?
Yeah.
Okay. So this week we'll talk about Bayesian modeling and probabilistic programming. And we have a very special guest today, Rob. Rob is a machine learning engineer and a data scientist. He's interested in deep generative models as well as good statistical models. Previously, he was a research scientist at Indiana University, where he worked on the Hakaru probabilistic programming language. Sounds Japanese, right?
Yes.
Sudoku Hakaru.
Yeah. It's actually a verb. So hakaru means to measure, and it was a system that actually took seriously measure spaces when modeling events. So it's kind of the name also in some sense advertises unique features of the library.
Only if you speak Japanese or understand.
Well, it's
Yeah. Okay. Yeah. So the questions for today's interview are prepared by Johanna Bayer. Thanks again, Johanna, for your help. And let's start. Before we go into the main topic, Bayesian modeling and probabilistic programming, let's start with your background. Can you tell us about your career journey so far?
Yeah, sure. So for me, I basically started as fairly regular like software engineer, computer science person, and I went to LA, sort of worked in different startups, and sort of was getting involved with sort of just as sort of machine learning was kind of really having, I don't want to say like a renaissance yet, but it was starting to really like pick up. And what do I mean by that? What I mean is like open source machine learning tools are actually getting good. Because before, I would say, you know, 2006, 2007, lots of machine learning tools, like they were very hit or miss. Like you had some nice stuff in the R ecosystem. And you had
Vecca.
libraries like OpenCV and things,
I remember Vecca. I
MATLAB,
used.
but like there really weren't like scikit-learn only essentially was created like I think in like the late 2000s, and it was actually very hard to do good machine learning work readily well. Um, like everyone was basically just it was all researchers, so everyone's essentially just rewriting all the algorithms from scratch all the time. But they were starting to get pretty good, and I was very much really engaging with machine learning. But I was often finding that like a lot of the kind of problems I wanted to work with, they didn't always fit things like scikit-learn or things that you could just throw a random forest at. Um, so I got interested in Bayesian modeling, and through that, an opportunity showed up so I can work with essentially a former university professor of mine, Ken Shan, in Indiana. And over there, I basically could work on probabilistic modeling, Bayesian modeling tools. And through that, I really came to kind of, really love and appreciate the power and flexibility of these tools. And so from there, I went, did PhD program at Oxford, where I kind of worked on more deep Bayesian modeling, so very much like VAE sort of things. And then sort of after that, I've moved to Berlin to kind of move back into industry, start actually applying these tools because, in some sense, I was motivated by, the problems I cared about with a lot of these tools are things that are very challenging to sort of, work on the side. They really are research problems that sort of require dedicated time. But I feel like, I became very motivated to sort of see these tools now get widely adopted, and I also just enjoy solving actual problems. So a lot of my trajectory has kind of been this, kind of back and forth, where I sort of pop into industry, dip into academia, pop back into industry, pop back into academia, as I sort of try to kind of push the technology forward.
And as a software, you said you were, how did you phrase it? Like a usual software engineer slash computer science person.
Yeah.
And I imagine that for a usual computer science slash software engineering person, when they see all these mathematical formulas from the Bayesian modeling, they just freeze or freak out or whatever. Like I remember for me, like, oh, all these integrals, like I don't understand what's happening here. Like, how did it happen for you? Like, how did you, like, was it easy for you to get into the field with your software engineering, computer science background? Or you had to to do a lot of extra work to be able to work and not to be afraid of all these formulas?
Sure. So I might be like, I might be a little bit not the typical case, because I always had a love for like machine learning and AI. So I kind of always knew that like I'd need to like be comfortable with like integrals, things like that. There are some people where like, they were software engineer, they were like used to like, making things like web servers and mobile apps, and then like they're like, calculus, I thought that was useless. You mean this math I was taught in secondary education is like, this is like the most important thing I could have known? Why did my teachers not say that? So they're like, I didn't quite have
They
that,
did.
because
I think they
kind
did say
of
that.
like, if I wanted to use these methods, I had to at least be somewhat comfortable with optimization methods, and like and linear algebra, and there's kind of no way to do that without being at least a little comfortable with like taking a few integrals, taking a few derivatives.
Mhm.
So it was less of a
Did
shock in that regard.
did your job as a software engineer? So as I understood, you started your career as a software engineer and then you transitioned to more like Bayesian stuff.
Yeah.
Like, did your work as a software engineer involve mathematics, or it was like creating websites and doing backend stuff
No,
and
no, no, no.
databases?
It was fairly like, it was very much like, scrape data from it was very much things like scrape data from the web, clean the data, put it in a database,
I see.
repeat.
So fairly standard
Yeah, yeah,
software.
nothing like, not so much as even calculating a median.
Okay, okay.
Uh,
So you kind of kept your, if I can say it, mathematical muscles fit by doing some extra stuff, or you
I
just
think it was
like
just like,
mathematics so much.
it was just like you're just sort of dabbling in the problems, you're reading about them. Because in some sense, like if you're like, oh, I want to learn machine learning, so okay, I'm going to learn how to like, run a random forest or implement the random forest. I'm going to implement, it's like you just sort of, it just spend a lot of time on the side, sort of getting comfortable with things, making little programs. This was back where there weren't these like very beautiful boot camps, which really, I think, try to structure a lot of this knowledge. So I was just dabbling. So I've told this to people. I've never taken a formal statistics class ever. Like I never did. I just basically just kept buying statistics textbooks until I felt sort of comfortable enough with the ideas.
Interesting. Yeah, for me, I remember my first formal machine learning class was a bit of a shock. Maybe not a bit of a shock, but like was actual. Like it was at TU Berlin, and the professor started with introduction to Bayesian modeling, with a lot of integrals and like the things we talked about, like this marginalizing, and he just assumed we kind of know all the stuff.
Right.
And it was like, okay, what am I doing here? But I decided to stay and see what happens. It was a good decision. But yeah, it was scary. Like, so for you like from the university times, you liked mathematics. You were curious about that. You were reading statistics textbooks. So that's why this is how you kept your mathematical skills, right? So for you, this transition, so from software engineering to more mathematics heavy stuff was not uncomfortable, right?
Right. Like I was already reading these things of like, oh, this is how you marginalize, and this is how.
I guess that's why you transitioned, right? Because you wanted to do more of that stuff, not scraping.
Yeah, in some sense, I kind of already did, but this was the thing where it was like at that point, like it was there, like thinking about like 2006, 2007, 2008. There weren't machine learning engineer jobs. That wasn't a thing that existed. It's there were analysis jobs, but like this idea that like you would be in a tech company like doing machine learning was like those jobs existed here and there. Like like they might exist in Google, like if you want to help with spam fighting or working on the ranking algorithm. But that was a machine so that was a job where you use machine learning, but you'd be basically hired as a software engineer. And you can sort of still see it like in like the culture of a lot of like companies that haven't really come back and like reflected on roles. It's just they hire software engineers and then they hope they can teach you statistics later. That's a culture that's I think still sort of persists quite a bit.
I'm pretty sure it does. Yeah, I see it. I see that. Like, there is an opinion that it's easier to learn the math you need than engineering. So it's easier to hire an engineer and then teach the math, the basics, and then let them work on the ML rather than getting them in a position to be a good engineer.
Right.
I don't know if it's true. Like, I've seen good people with.
Yeah, it's not clear if it's true because I've gotten to experience the opposite, which is you have a bunch of to put it bluntly, you have a bunch of unemployed physicists that know the math and basically are taught software engineering. And my personal experience is they do just fine.
Yeah, I'm pretty sure. Like, if you know all this, because like physics involves a lot of mathematics, right? Like all this gravitational stuff. Like, if you look at that, like you're just the variety of symbols there and Greek letters and all that stuff, it's even scarier than the integrals, right? And then they understand all that, right? And if they understand all that and can make sense of that and spend like 5 years defending PhDs about that, and for them, like learning Java is not that difficult, right?
Right. Yeah. So it feels like such a silly, like I don't know. It feels like I suspect that the reason this attitude is taken is more because software companies are run by people who used to be software engineers. So, that's what they value. So their attitude is software is what I know. So software is not what I expect to teach. Statistics is something I don't know. I kind of had to dabble and learn. So that's what I'll expect of the people I hire. Like, right. I feel like it actually just flows downstream from those kind of unstated values.
What is Bayesian modeling? What are we talking about today?
Right. Okay, yeah. So also, like, I've been saying the words probabilistic modeling and Bayesian modeling. They're not quite the same thing. There are differences. So if you take a statistics class, maybe this is changing, but like if you take a statistics class, at some point, I don't know, it feels a little bit silly to say this considering I never actually formally taken one, but I read a bunch of textbooks that are used for these classes. So hopefully this is like, hopefully I'm not coming off too presumptuous. Okay, let me say it this way. If you open up a statistics textbook, an introduction one, they'll often say there are these different schools of how to do statistics. And what they'll basically say is they'll say there's this sort of frequentist modeling approach and a Bayesian modeling approach.
My statistics class started with that, yeah.
Okay, good. Oh, okay, all right. I don't want to be like, oh, this is how a class starts. And I was like, no one does that anymore. They shouldn't, but so it
was a long time ago though, but yeah, I confirm.
Yeah. So they'll say there's frequentist modeling and there's Bayesian modeling. What do they mean by this? What they mean is in a frequentist modeling approach, there's an assumption that you have a parameter that you're interested in. So you're interested in, say, something like annual rainfall in Germany. So this is like an actual quantity that exists in the world. But, there's no way to directly measure that. But what instead you can do is you can measure things that are sort of noisy they're the result of processes downstream of that. So you can do things like, measure soil or sort of, measure like increased water and sewage systems. These aren't annual rainfall, but these are essentially quantities that you can then use to estimate annual rainfall. And there's, of course, some noise, there's some variance. So a lot of what frequentist modeling is about is we're going to essentially do these data collecting processes for these, and then use that to estimate. And then because there's some noise in that, we can't say this is what annual rainfall is. We essentially give you a confidence distribution, which is that here's what we think it is, and here's like some bars of where we think the value is. So, so you'll say things like we're 95% confident that the true estimate of annual rainfall will be between these two values. And frequent statistics is nice in that regard, in the sense of like these confidence values mean something. What they mean is like if you do 100 experiments where you gather data and then estimate the rainfall, your estimate 95% of the time will be between those two bars. So like there's really good guarantees there. But that's frequent statistics, which I don't really do. There's there's also Bayesian statistics. And Bayesian statistics actually takes a very different attitude. Bayesian statistics does not say, in Bayesian statistics, there is no point estimate at any part of the analysis.
And by point estimate, you mean like we make an experiment?
This just number where you say, this is what I think the annual rainfall is.
Yeah, so we get a number and this is our point estimate of the rainfall, right?
Right.
And then we put some bars around it to say, okay, and like this is the interval, right? So then it's still point estimate, right?
Right. There's a point estimate and then there's a confidence interval around it. So there are things that use this distributions in frequentist statistics, but for Bayesian modeling, the fundamental object is a distribution. You almost never are doing anything with point estimates. So everything has a distribution. So before you even begin, you don't even talk about, oh, I want annual rainfall. You say, I have a prior distribution. So I have a starting distribution of what I think annual rainfall is. You know, and what you then do in Bayesian modeling is you then collect data, and then through basically applying Bayes' rule, you end up with a posterior distribution of rainfall given the data you've now observed. So it's always distributions. You're always working with distribution. You never. What's the advantage? Say what?
Oh, so let's say I have some assumptions about rainfall, annual rainfall in Germany. It could be, if I have zero clue of what it is, it could be, okay, it's a uniform distribution between X and Y. I don't know, some numbers, right?
Oh, sure.
Like I have no clue, and then this is the starting point, right? And then I go and dig a hole and then measure something, right? And then I get some data, or go open, like,
right,
look into the sewers, and
right.
there's some another variable, right? And then I collect data, and then from the flat line, from uniform distribution, I start getting something else, right? And then this is what I do with Bayesian modeling.
Yeah, so Bayesian model, yeah, exactly. You would start with some example like that. It's now I would hope you wouldn't use a uniform, because you've sort of collected some data. You've looked at some annual rainfall estimates over the years, and you said, like, oh, it seems to, sometimes there's less, sometimes there's more.
It all depends on what kind of data we already have, what kind of knowledge we already have.
Yeah, of course. But the important thing, it's always a process from one distribution to another. Now, why would someone prefer that? This feels like, a little bit more, it seems like more work. And it is work, because doing this Bayes rule over and over again often involves computing a lot of these annoying integrals that are often like not efficient. But what's the actual advantage here? Because it's distribution in, distribution out, it's a very composable framework. It's very easy to like extend your analysis and sort of build up an analysis, because everything is just distribution in, distribution out. So it's very easy to sort of, because here's the thing. I have this distribution on data. That can be the starting point for a future analysis. I want to add more variables into the model later. I can start with this one, add in a little bit, where I sort of now observe more data, and it's very composable. It's in that way, where it's very easy to sort of start from a simple analysis and incrementally build into a more complicated one. Where often in frequentist statistics, you can't really do that. You often have to kind of throw away a lot of your old work. So, what this often leads to is, because you can sort of build up your analysis, you can sort of write tools that sort of do this compositional work for you. And that's kind of like, and it becomes much more amendable to these sort of universal solutions, where you can write a model, kind of derive a sampler from it, and get to work. So in that sense, it's very useful in that regard.
And how is it related to probabilistic programming?
So probabilistic programming are effectively tools to make doing Bayesian modeling significantly easier by removing all the tedious steps.
And tedious steps are computing integrals.
It's computing the integrals or approximating the integrals by sampling. It's figuring out which integrals you have to compute when you write your model. It's all these little steps that they're sort of straightforward to do, but they're very tedious if you have to do them again every time you make a little change to your model.
And why computing integrals is such a big deal? Like why we just don't compute them? Like, what's the problem with them?
So the issue with the integrals is like if you go to like an introduction calculus class, there's this impression of like you're going to write this integral, you're going to write this formula, you write an integral, and look, it has this nice clean form. But of course, the tragedy there is that this is actually like not the common case. The idea that I could just write a function and get a nice integral from it is not what actually occurs. They just don't often exist. In some sense, it's the opposite of the case you have in derivatives, where there actually are very nice ways to automatically calculate derivatives. So like when you use PyTorch, you could just write a function and be handed essentially another function that computes derivative. No such thing really exists in integrals. So what people have to often do is they have to approximate that. What do we mean by approximate? So if you remember when people talk about Riemannian, where you sort of make these little bars and then you sum the bars, people effectively have to do things like that. So like,
which you mean compute the integral numerically instead of computing it, how they call it, analytically, like when you see it with
instead of
paper,
like
use rules to derive the formula. You cannot do this because for some cases, like there is no rule that you can apply here. So the only thing you can do here at the end is just use numerical methods, which involves summing one thing. Like I remember, usually integrals are would be from minus infinity to infinity, right? And then like you need to, okay, how do I compute it numerically, right? So it can be computationally intensive, correct?
Right. Yeah. So, but effectively, this is what we're kind of doing. Like we're kind of going in and like we're computing numerically. So like often what happens when you're sampling, you're approximating an integral because you're like, okay, I have this curve. I'm going to use probabilities to land on different parts of the curve, and I'm going to count. And that's effectively, by counting them, you're essentially like, it's almost like building the histogram, right? You sort of like, you're making each of the bars and you're counting what each of the bars are. So a lot of times when you're sampling, you're essentially just approximating this integral. So that's a lot of what the regime is. So in Bayesian modeling, because most of these integrals are intractable, we devise these sampling methods.
Intractable, you mean we cannot compute them on a piece of paper, right?
We can't take a formula, get back another formula, and then essentially, pass the bounds of integration in and do minus and then repeat if we have nested ones. Like that's like an option that really doesn't exist for the kind of integrals most people care about. Sometimes provably so. Like if you look at some of the integrals that are involved for these probabilistic models, like, you're getting things like the error function. And, people are like, what's the error function? It's this integral. Does it have a closed form? We've never found one. Or we've proven that one can't exist. Or they use to say these functions, these nice set of functions. So you have to do these numerical methods. You have no choice.
So again, if we go back to our discussion of Bayesian versus Frequentist, so in Frequentist, we get a number and then confidence interval, and that's all we get, right? In Bayesian, on the other hand, we start with the distribution, we end with the distribution, but because we deal with distributions, we get all these nasty integrals that we have to deal with somehow. And this is why we use probabilistic programming, because otherwise, if we just directly use numerical methods to compute these integrals, these things you mentioned, like histograms, like it's just takes too much time, right? That's why we have approximation methods that do faster.
Right. Well, there's two things. One, without probabilistic programming tools, for every model, you have to essentially figure out what the sampler is going to be and then write it. And if you make your model a little different, you have to change the sampler. You have to rewrite. You have to make a fresh. What?
What is a sampler?
So a sampler is this. it's a way to sort of figure out these integrals by basically you're going to sort of sample from the distribution in a particular way, and that's from the posterior distribution, and that's essentially going to give you a bunch of draws, which you can then take the empirical average of, and that's going to essentially let you approximate the integrals that are involved for.
So posterior distribution is the result. This is the thing we're interested in. We cannot easily calculate it because there is no formula, so we need to somehow figure out what's the value there, right? That's why we need sampling. There are different samplers that different approaches for computing this integral, right? So these are the samplers.
Yeah.
So Monte Carlo simulation is one of the possible samplers, right?
Right. Yeah. So what I think what happens is sampling is its own challenge. So what you quickly realize is if you try to do this the naive way, most of your time, like if you just said, I don't know where my distribution is, I'm just going to guess randomly and then check, you will find that particularly in high dimensions, most of your guesses are going to be in low probability regions.
I have no idea what this sentence meant to be.
So like, if you're trying to guess rainfall and you know it's some number between 0 and infinity, you might find that you often spend a lot of your time generating a guess that has low probability.
So like I think, okay, maybe it's 1,000, whatever unit is, like, but it's very slim chance that it's actually 1,000. And no matter what number I take, the chance that I'm correct is still
now, you could use your prior distribution, like that uniform example, and use that as a guess, and then essentially do a reweighting, and that's better than guessing completely arbitrary. But if you think about it, like that's just in one dimension. Now imagine in like say 1,000 dimensions or 1,000,000 dimensions.
And dimension is in this case would be like rainfall would be like one dimension, right?
Well, but like imagine you're trying to now estimate rainfall for like not Germany, but sort of every city in Germany.
Okay.
And there's clearly relationships between them. So like, a guess for one is probably not a bad guess for others. But it's but if you're just guessing arbitrarily, the chance that you're going to pick up thing with reasonably high probability just goes down tremendously.
Like even if we pick only like, I don't know, 5 largest cities in Germany, and then the probability that we pick the rainfall for each of them correctly is non-existent. But like, okay, we might get lucky, but if we add another city to that, with each sector,
just as you increase the dimensionality, like the chance that you're going to kind of do okay. And of course, you can keep running samples and hope that eventually you hit high probability regions. But that takes computation time and like.
And by running samplings, you mean like, okay, we have these 5 cities. Let's just roll, I don't know, 5 dice.
Yeah.
It's the plural. 5 dice, whatever. Like we just go to open our NumPy and ask NumPy, okay, get us 5 random numbers between 0 and infinity, right? And we repeat until it's correct, right? That's what
you can sort of, like it could take a while to like actually get answers that have like a high probability. So
but how do we even know that these are correct if we just get them?
Our model essentially returns to us what's the probability the parameter has this value given the data we return. So we have these probabilities there, but we can't in advance know like what's going to be the high probability regions. There are tricks, right? You can sort of take the maximum, the maximum a posteriori of this function and say, okay, what particular set of parameters gives me like the top one? But again, that's a point estimate. That's kind of what fruit. You still need to look at what are other likely values. Also, the maximum a posteriori can be deceptive for lots of problems. So all of these fancy sampling algorithms, they're all tricks to make it so that when you sample, you're likely to be sampling from a high probability region. So, so that's where you get things like MCMC. So, what does MCMC do? It says, well, pick a starting point and make a small move from there.
Is Monte
Markov chain Monte Carlo.
Monte Carlo, yeah.
Yeah. So Monte Carlo, because you're sampling, it's gambling, you're throwing dice. And then Markov chain, because each sample that you pick is dependent on the previous one. So they kind of form, there's kind of a Markov chain of all these samples. So when we say Markov chain, and why is Markov chain Monte Carlo work fairly well, particularly in high dimensions? Because you assume that your high probability points are near each other. So for annual rainfall, if we think like something like 50 centimeters of annual rainfall is a good estimate and has good probability, we expect 49 is not too bad either. So you can you start there, and then your next sample is near there. You make a move that's in the region. And in that way, you sort of hope to stay in the high probability regions of the space. And then you can say, okay, well, this sampling algorithm, it has shortcomings too, so we make a better one, and so on and so forth. But the whole development of sampling algorithms, it's all for the purpose of getting points that are in high probability regions of the space without spending too much computational time doing so.
And that's what you did when you developed Hakaru, the Hakaru language, right?
We didn't actually develop new sampling algorithms for Hakaru. We just took some of these algorithms that were out there and made them so that the users didn't have to run the algorithms. The user just ran the model and they got the algorithms. That's the main thing that every probabilistic programming language is doing. It's just about letting someone talk about their model and writing the sampling algorithm for them.
And what do we actually mean by saying it's a programming language? It's like there is Java, there is R, there is Python, there is Hakaru, right? So you actually write code there. It's
you write code.
It's an interpreter, different environment. So it's not Python, right?
Right. Right. Well, it's not quite Python, but it's...
Or these sort of things that we've been talking about, right?
Yeah. So what we mean by that is when we think about statistical models, sometimes you'll think about the professor writes some notation on the board. They say, I have some parameter. It comes from this distribution. If I see this value, it comes from this. But if you just kind of pause and step back a bit and think about what a statistical model is, think about just using just the annual rainfall example. I might say, I expect a certain amount of rainfall in a region just because it's in a particular latitude and longitude, and I expect some regional variation. And why do I expect some regional variation? Well, some towns, they're near a mountain, and mountains affect things. Some towns, they're just maybe a little more south, so it's a little warmer, so they get more. And if you think about how you would write that model, thinking about, it's neat. I have a loop. I iterate over cities. I have if statements that I check whether I have a mountain. Some of these parts of the model might be tedious. I might create subroutines. Oh my God, we have a programming language. This is clearly a programming language. Just by virtue of trying to talk about what you're modeling, you inevitably are using a sort of language to do so. And so from my perspective, this model, the way we talk about modeling, is a programming language. So what we do with
scikit-learn, in the same sense as scikit-learn, we can say it's a programming language because there are what's the difference between a library and the programming language? I guess this.
That's a very beautiful question. If you talk to some people out of like the University of Utah or some of the racket scheme people to say this distinction between a library and a language is it's not very black and white. There is a little bit of in between. So I think the distinction can be a little bit, but I'll make the case that there's this notion of ifs and subroutines and looping primitives. These are things that we associate with languages, not libraries. Like a looping primitive isn't like a thing you use within scikit-learn. It's a thing you use within Python, which you then call scikit-learn from. So when we talk about a statistical model, like it's not just that we're using an if in Python. It's that, like when I talk about, oh, I think the rainfall should be higher if a town is near a mountain, that actually affects how we compute the probability of there being rainfall in a particular town. So it's not just that we run a simulation, it actually has consequences into how you compute the log probability. And if it has consequences like that, then it's like, okay, we're not really evaluating this if, we're interpreting it differently. But if you're interpreting differently, you're not in Python anymore, right? Like clearly this if is living in a different space at that point. So I think it's actually useful to say, oh, this is its own language, which we can embed in Python or R and what have you, but it's definitely its own language with its own semantics.
And scikit-learn is not, because we don't use ifs.
Because we're just calling we're just doing these API calls. There's no notion of like a new sort of if or a thing like, like a unique notion of a control flow.
Well, it's still a little bit abstract for me, to be honest, but yeah, maybe I should read those Utah folks, right? You said that there is University of Utah who are really into programming languages, and
yeah. So
they probably have a course about
papers that are things like libraries as languages and things like that. So like you import a library and you get a new language, or you have a language that slowly turns into, you have a library that slowly turns into a language. So there are these like notions that you can. The distinction isn't like there is a gradient between these two. But from my perspective, scikit-learn has an API. It has function calls, it has data types, and they can kind of be moved together. It is a language in a certain sense, but it's a very restricted language. And because it's so restricted, I think most people are comfortable calling scikit-learn a library more than calling it a language.
Okay, what's PyMC?
Right. So PyMC is one of the major probabilistic programming languages / libraries in Python.
Just libraries. Interesting. Okay.
Well, it's a library because the Python library, but it very much has its own language. So like when you write a model in PyMC, you get a computational graph back. You get an AST. So like, which you can inspect. Like it's very, so when you write models, you use Python code to write them, but what that Python code is actually doing is like building up this computational graph, which is effectively an AST.
Okay, I am lost. Like, how does a PyMC, can I say, program looks like? So let's say we want to estimate the annual rainforest in Germany. Rainfall in Germany.
Yeah.
So we want to use PyMC for that. How does our program look like?
So the way it would look like is you would say, let's just pick a very simple example. Let's use a simple model just as an example for now, which is we're going to assume that there's a certain annual rainfall we expect in Germany, and we're going to assume that all the cities essentially are that rainfall plus a little noise, which isn't the worst assumption. the way you would write that in a PyMC is you would write, Germany rainfall equals normal, left parenthesis, as an example, the mean rainfall, comma, the standard deviation we expect on the rainfall. Now, that's not exactly how you write it, because the syntax in PyMC requires that you put a string, so you name
Probably
it.
very difficult to also explain it without just by talking.
Yeah. But at a high level, this is effectively what you do. Now you might say, okay, rainfall is never a negative number, but I will hand wave that and say that when we're going to use a good sampler, so we're gonna try never to sample negative numbers. But there are distributions.
Say if sample greater than or less or equal than 0, then sample one more time.
Yeah, we can do something like that. Also, PyMC has a thing called the half normal, which is just the normal, but we just chopped off a part of it. So there, we can do that as well. But we're gonna do that, and then we're gonna have and then the next line is gonna be, we're gonna sample annual rainfall for every city, and that's just gonna be rainfall for cities equals normal, left parenthesis, mean, the global mean we just estimated, comma, so much variance we expect for each of the cities to have, comma, shape equals number of cities, right parenthesis. And then at that point, we're then going to add another thing, which is, we'll say
just
sewer level for each city. And we're going to say the sewer levels there's some function relationship between them, and we're going to essentially call that annual rainfall thing, pass that through that function to get them, and then that's what we're going to actually observe, because what we observed is how much sewer levels rose for each of the cities.
So what we're doing here is some sort of linear regression, but instead of just output for each city, we get a distribution, right?
It's not quite a linear regression, right? Because
we have some features, right? Like this stuff from sewer.
Because we have this parameter that we're going to be using to sort of try to keep all the rainfall values near this global value.
Yeah, that's why it's kind of sort of conceptually like linear regression, or more like just regression, right? Because we predict, we output a number or a bunch of numbers, because it's a bunch of this. So conceptually, it's a regression, except it's not linear regression, right?
Right.
It's a different sort of regression model that outputs probabilities, or not probabilities, like distributions. And we have this ability to say that this is the global mean, and it shouldn't be too different from the global mean.
Exactly. So I wouldn't quite call regression, because you can represent regressions in PyMC. You can say, you can say that there is you have some x, you have some y, and we have some relation between them. This function has some weights. I don't know what the weights are. We're going to put a distribution of weights. So you can't do regression. This isn't quite that, but the intuition is that you have this model that can say there's rainfall, there's a relationship between rainfall in these cities and the sewage levels. There's a relationship between rainfall between cities because they're kind of near each other. And those are all, you can just readily encode them. And this is just a 3-line model, but already there's already kind of quite a bit of richness there. And of course, that's just the model. Then you probably want stuff. You want some quantities to come out. You can then call, PyMC.sample to now get estimates of all these city rainfalls. You might care about also the annual one. You might ask for that one as well, since you've already modeled it. And then when this runs as samples, you will now have a posterior distribution on rainfalls for each city and for just this estimate of what the rainfall is in the country as a whole. And at that point, that's pretty good. Now in practice, you wouldn't just stop there. You might actually pull up like statistics of actual previous estimates people had of rainfall. And if your estimate was too far from these like, government records, there's something probably wrong with your model, and you would make the model slightly different. You might add other parameters than just measuring sewage rises. But over time, your estimates would start to match the kind of estimates that others had, and you can feel confident. You can sort of have confidence that you seem to have captured something.
So from what I understood from what you said, PyMC and probably other probabilistic programming languages or frameworks, what they give us is the ability to express our problem in some sort of language and express dependencies between different things. So we can say there is some, can I say, locality dependence? So like cities that are close, they probably shouldn't have two different
right. No, the model I just said
global
says
so in your case, so in your case it was so they shouldn't be too different from the global.
Exactly.
Which kind of captures that, right? But you can make it more complex, saying that cities that are close.
Yeah, so you can write you can start doing like spatial models where you say like cities that are close to each other should have similar annual rainfall, and there are ways to sort of encode that.
Like how far it is from the sea, right?
Right, you can encode how far you are from the sea, for amount. Like you can start quickly building up. And what's nice is, what does it mean to build it up? You just add another line of code, hit sample again. It's the process is much more natural. You're not, I want to model what it means more far from the sea. Now I have to sit, recalculate by hand thing. I have to check if I can still use the sampler from before. Am I doing something where suddenly my old sampler is not good? Do I need to make a hack to get around that? These are all things that used to be the norm. Now people, by and large, they write in something like PyMC or other probabilistic programming languages. The things like Hakaru, Turing, Stan. There are many of these sort of.
And if I compare it to, let's say, can I say classical frequentist approaches, right? So when we, let's say, have linear regression problem, it's, let's say, random forest or whatever, and then our features would be all these things we talked about, plus maybe how far this is, right? So if we want to introduce one more thing in our model, in our problem, I don't know, distance from the sea, then in the frequentist case, we just would add another feature, the distance from the sea. And in case of probabilistic programming, we would model it differently, right?
Yeah. Now, it might be you add another feature because, you're doing something like a Bayesian neural net, and you just add another weight, you put another prior on that weight, and then go from there. And, you just say, this is just going to be distance from the sea. How important is this weight? So you can do that as well. But if you're trying to do something where you're doing these groups, it becomes actually kind of a little bit tricky to do. So if you're trying to do things like, say, dynamically turning on and off groups of features, that's a thing that's actually quite subtle to do using machine learning algorithms. In a probabilistic programming language, that's just another line of code. You're not even thinking about it. You're just yeah, let's group things. Who cares? You're not even thinking about, oh my God, this tiny change I made has severely changed the algorithm, and I can't use the one in scikit-learn anymore. Also, we should keep in mind that by and large, for these prediction algorithms, there's no distribution. It's just, here are my inputs, here's my outputs. And maybe if you're lucky, you might get a confidence score on that output. And if the confidence score is too low, you might say, okay, maybe we should be careful with the prediction. You don't get this distribution where I say, you've given me this input, here's a distribution on the values. And this becomes particularly relevant when you start getting these multimodal distributions, where you can say, there isn't one good answer. There are two good answers that are very different from one another. Because, you might say things like, well, when there's a drought, the rainfall is very different than when there's not. So if you're just asking me what the rainfall is, I can say like, well, in drought years, it tended to be this number. In normal years, it tended to be this number. That is the thing that's very easy to express in a Bayesian modeling framework and very difficult to express outside of it.
And you mentioned when you were talking about different probabilistic programming languages, frameworks, you mentioned Stan, right? So, and then there's a question from Johanna. What do you think about Stan? So what is Stan and what do you think about it?
Sure. So Stan, I think I can comfortably say this, is the main and most predominant probabilistic programming system out there. It's a pioneer in many ways, which I'll explain shortly. It's a leader in the space. It's the main one. If you only look at one, you should look at Stan because it is the main and dominant one. And why is that? So part of what that is there have been probabilistic programming systems before Stan, but Stan it did kind of two things. One, it introduced HMC into sort of popular use. Hamiltonian Monte Carlo. For the moment, I'm not gonna go into like what makes HMC like special, other than to say it's a significantly better sampling algorithm than all the others that were previously in use. It is so much better that if your problem doesn't fit HMC, the advice is figure out a way to make it work in HMC. Like, it's that good of a sampler that, it changes the gravity around the way you model things. And so if you're using Stan, you're just getting better estimates, better results than if you're using other tools before Stan kind of came along. And this trend continues. Innovations in sampling algorithm often first appear in Stan before they appear in other systems. This isn't fully the case, but this is the case often enough that it's true. And it really and the best practices established in Stan set the tone to best practices used elsewhere. So if an algorithm gets introduced in Stan, it'll likely appear in PyMC within a few months, and others like it has there's a strong leader role there. The second reason, of course, is that the algorithms that Stan uses tend to have a lot of their own hyperparameter tuning, so they work out of box. So you're not doing lots of fiddling. There really is just kind of this button called sample that you hit, and you get samples out. You're not like doing these little tweaks where you're playing with little parameter numbers to kind of make it work. Because HMC has existed for decades, but it required you to know these very particular arguments that you had to pass in. And if you got the arguments wrong, it didn't work at all. But getting them right was very fiddly. So Stan added features where they figured out what were the correct arguments to pass to HMC. So when you have things, it's called the no U-turn sampler, NUTS. The main thing NUTS is doing is it's taking HMC and figuring out the right parameters to like use in HMC for your specific problem. And because of that, you essentially had this sampler that was very efficient and required basically little feedback to work. And yeah, I think Stan's great. Like, I'm not gonna like say anything other than that.
And I was just checking the questions, and so the reason I was asking about PyMC is because you have contributed to PMC. You're a contributor to this library. So thanks a lot for doing that. And yeah, do you have a couple of more minutes before we finish?
Of course, yeah.
Great. So, like, we have a course. It's a machine learning engineering course, and the way we do it is half of the content is about machine learning, and the other half of the content is about engineering. So the half about machine learning, as you can imagine, is about the frequentist approach. Like first we start with linear regression, then we talk about logistic regression, then we also cover tree methods, and then we cover neural networks, right? And then I imagine that our interview, our chat, some students will listen to our chat right now, and some of them might wonder, okay, we now have learned these approaches, like these frequentist approaches, but I want to try something Bayesian. So what would you suggest for them do? Like, what's the easiest way for them with the background they already have to try something Bayesian, like maybe with PyMC?
Sure. So, so there's a book I like. So this answer has gotten much easier in recent years because people have really started to produce good materials for this. It wasn't as because before I would have said, oh, you should just like buy a book on Bayesian statistics. I'm gonna still say that, but the books are better now. So I'll suggest two things. There's a book on Bayesian computation that was written by a lot of the PyMC people. So as Raveen Kumar, has as Waldo Martin, and a few other people I'm blanking on. And the book's freely available online, and you can sort of work through it. It uses PyMC to sort of explain how to do Bayesian statistics. There's also an online book that's a little older called Bayesian Statistics for Hackers. It also uses PyMC. But if people like a course environment, there's a really amazing course taught by Richard McElfrey, who's out of Leipzig, called Statistical Rethinking. And he has an online course. Previous versions of the course are freely available on YouTube. So you can just watch the course online there. He has a book. The book isn't free, but the book's very good. And his book is really amazing. I think it's hard for me to I'd be hesitant to say anything wrong with the book for what it does. Because what it does is it doesn't just teach how to do Bayesian model and Bayesian statistics, it teaches how to do statistics. And a lot of the challenge of doing statistics is often not, oh, should you do frequentist or should you do Bayesian? It's often like, are you capturing causality properly? Are you collecting data in a good way where you'll actually be able to like learn something, improve your models? It really kind of takes this big holistic view, which I think
instead of saying one is better than the other, it just says, okay, like here are the problems, here are the things you need to think about, and here are the solutions, right? The tools you can use.
It really teaches the workflow, which is really where I think statistics really can be lacking, is that too much of the old ways it was taught were like they were cookbooks effectively. Here's your problem at the factory, use this recipe from the cookbook, which, because of the dynamic way we work with data, like the idea that you could like do a cookbook for a data science test, I feel is very like it's overly optimistic, I would say, for a lot of the challenges people face. And where I think this book shows its strength is it says, here's the attitude you should take for how you should be doing statistics. And if you have this attitude, you'll figure out the correct steps you need to do to get an analysis that's useful and actually informative. So I recommend the Statistical Rethinking book/class, and particularly for PyMC, I recommend the Bayesian computation book. I found up there.
Sorry?
That all the like programs that were written in Stan for the Statistical Rethinking book have been ported to PyMC 'm-C by enthusiastic volunteers.
I found so first the book is called Bayesian Modeling and Computation in Python with
Yes.
authors Martin, Kumar, and Lau. I posted the link. And then the
Yes.
second
That's
one,
the book.
Statistical rethinking. The author is Richard Mack. I can't really
Yes.
see. Like it's very tiny, but like I just posted the link. So I don't want to try and butcher the author's name. The examples are in R and Stan. Okay.
Right. Yeah, he
And you
provides
said like the enthusiasts ported everything from that book
yeah,
to PyMC.
yeah. It's the book is so good that students find it and then port the examples to PyMC.
Yeah, we should be wrapping up. So it was amazing. Thanks, Rob. So you made some things clearer to me personally.
Yeah.
Like sometimes you would say something and I would just, okay, what is it? But now it's clearer. Thanks. And maybe before we wrap up, like, is there anything you want to mention?
Yeah, sure. So yeah, this may be a little bit of a plug. So I do statistical consulting. It's kind of the main thing I do these days. I write software as well to help with that. But yeah, if for anyone that's listening to this, if you or your company have statistical challenges, are actually interested in maybe applying Bayesian modeling for your problems, reach out to me. I'm always interested in helping people out on this.
What's the best way of
The
reaching
best
out?
way is just to email me, rob@zinkov.com.
Okay, so we will include also the email in the description. And I posted 2 links in the live chat. I will post them also in the description. And yeah, I guess that's all for today. Thanks a lot, Rob, for joining us today. And thanks everyone for joining us today too.
Yeah, thank you.
Everyone, have a great week. So see you around.